All right. Good morning, everyone. We are live. First of all, can someone kindly let me know in the chat? Can you hear me? Can you see the screen? Can you let me know in the chat? I believe everything's okay. It's been working so far. It's been working for 2 weeks, but you never know. You never know. Awesome. Thank you, Gabriel. Well, folks, if you are watching the recording, you're not with us live, the lecture will start at about the 15-minute mark. So you can skip ahead in the video for a while. But do give this a try. And those of you live, of course, give this a try. Decompose the following rational functions via partial fractions. Okay, this is the topic of yesterday's lecture and also today's lecture. Okay, this is supposed to be a light exercise, so you don't have to find the values of the unknown constants for this particular exercise. Okay, we know how to do that. That's all about solving a system of linear equations. We can do that. But this is the new part, so to speak, of chapter 2. So go ahead, give these 3 problems a try. I would like to know what you think, so please share your answers in the chat. It's going to look a little on the ugly side. That's okay. We work with what we have and do what we can. I will be here if you have any questions. Otherwise, we'll see you in 14 minutes. Give it a try. Has anyone decomposed the first rational function yet? If so, what'd you get? There's no worries about right or wrong. This is not a test. This is not an assignment. Did you get it? Let me know in the chat. All right, Fred's got an answer for. I should have numbered these, but yes, the first question. And you don't have to find A, B, or C. For this particular exercise, we will practice finding A, B, and C, finding the constants in 7 minutes once we begin. I won't give away any spoilers. So, what do you think, folks? Do you agree with Fred? Do you disagree? What do you think? All right. Gabriel agrees with Fred. And that's an easy way to input your answer, isn't it? The math doesn't look great with this basic chat function. But so far we have 2 people that agree on problem 1. What do the rest of you think? Do you agree? Do you disagree? What about question 2? That looks a bit different. What about question 3? That looks very different. We have 5 minutes, just under 5 minutes. So let me know what you think. I am here. If I don't hear from anyone, I will see you at 9:30 sharp. All right, got some answers for 2 coming in. Not easy to write out type out on the chat. Thank you, Fred. Gabriel agrees with Fred again. Well, that's a good sign. I won't give any spoilers. We have just under 3 minutes remaining. Can you do question 3? Do you have time? Do you have time to do question 3? That one's a little long, isn't it? Maximum effort from Gabriel. Well, he might have the same exact answer. That's what I'm guessing. He agrees again. Yeah, it's one thing to write it out with your pen and paper, but to type it, that's not so nice. Be easier if you had microphones on your end, then you could just tell me. All right, it's just under 2 minutes. Still have time, folks. Do you like Gabriel? Do you agree with Fred, or do you disagree with 1 or 2? Have you given question 3, a shot yet? Do you have time? I think you do. Trying to read Fred's answers. It's a little tough with the chat. Okay. Macabo, I just saw your answer. You don't agree with Fred, do you? So we do have some disagreement. It's 9:29. The suspense builds at 9:30 sharp. I will go over the solutions. Does anyone have question 3 done? You just don't want to type it. Another agreement with Fred. Okay. Three is too long. I understand. Yeah. Not too long to write out, but to type into the chat. I think that's what you mean. Gabriel agrees with Fred once more. Well, I agree with Fred too. It is 9:30, so good morning, everyone. We'll go ahead and begin the lecture. I definitely agree with Fred and Gabriel on question 1. This is how you decompose. Okay, these are 3 linear factors, so they get constants on top. Okay, and these linear factors aren't raised to a power, so we don't have to worry about repeating factors. Cool. What about the second question? I also agree with Fred, like Gabriel. And x squared plus 4, that's an irreducible quadratic, isn't it? So it gets linear factors on top, not just a constant, not just an a, not just a b, not just a c, but linear factors, ax plus b, cx plus d, ex plus f. Okay, it is raised to the 3rd power on the left side, so I have to keep going with this pattern from yesterday until I get a 3rd power on the right side as well. All right. Good job, Fred. Good job, Gabriel, for agreeing with Fred. This one, I hope you did it. I hope you did it, although I do understand this is not fun to type up in the chat. But 7x plus 8, that's a linear factor. So it gets a constant on top, okay? And I repeat the pattern until I get the 3rd power, continuing with the constants on top. Okay, done with that factor. X squared plus 1, that's an irreducible quadratic. It gets linear factors on top. I keep going with the pattern until I get a power of 2. X squared plus 8, is also an irreducible quadratic. So it also gets a linear factor on top, hx plus I, and it's just a power of 1 there, so I don't have to go past that. Hope you agree with me, and thank you all for participating. All right. So that brings us to the lecture. Same section, 2.6, an application to integration, part 2 of 2, okay? Last lecture on chapter 2. I'm Dr. S. What have I been teaching you regarding partial fractions? This is what I've been teaching you. I've been using a 5-step method to teach you these partial fractions, okay, which help us integrate, as you've already seen. So these are the same 5 steps from yesterday. Nothing new here except the very bottom, which is a little warning, a little unfortunate news, if you will. These steps don't always work. They often work, okay, but they don't always work. Let me give you an example where these 5 steps don't work. All right, let me zoom in a bit. Let's compute this integral. We'll call it k for short. Okay, well, it's definitely a rational function. Okay, it's definitely not easy to integrate directly, so it is not a bad idea to start going through these 5 steps. Okay, step 1, compare the degrees of the numerator and the denominator. Again, we call the numerator p, the denominator q. Okay, the degree of the numerator is 1, degree of the denominator is 2. 2 is larger than 1, so no long division required. Okay, I still owe you an example where it is required coming up soon. I can't help but notice that the denominator, q of x, is irreducible. 16 minus 20 is definitely negative. Okay, so at this stage, let me not spoil, but I think we should try step 3. Okay, let's see here. What do we have? We have 4x plus 13 over x squared plus 4x plus 5. This is an irreducible quadratic on the bottom, so it gets a linear factor on the top. Right? I'm just doing what I'm supposed to do so far, but maybe this looks a little strange to you. Maybe this looks a little strange to you. Wait a minute. 4x plus 13 over x squared plus 4x plus 5 equals ax plus b over the same denominator? Isn't it clear what a is? Isn't it clear what b is right off the bat? I think a's got to be 4. B's got to be 13. Right? Let's write that down. A has to be 4. It's clear. B has to be 13. It's clear this time. Okay, so I can plug those in, and then I get what I started with. So this technique isn't helpful for this particular problem, okay? You will run into this on occasion, okay? Where this 5-step technique, this partial fraction decomposition, if you will, just is not helpful, okay? So, folks, right now, we are stuck. The 5-step technique of partial fraction decomposition is not helping, okay? I haven't done anything wrong, it's just not helping. But what did I say, those of you that had me in tutorials last semester in 114? I said you could always use algebraic manipulation if it helps you. In fact, you can always use any kind of manipulation if it helps you, okay, as long as you do the manipulation correctly, okay? So, with that in mind, let's try that. Let's try some manipulation and see if that works. Let's see. I'll give you a hint. Doesn't our function 4x plus 13 all over x squared plus 4x plus 5, doesn't it look kind of sort of similar to the derivative of the natural log of absolute value of, well, the denominator essentially, x squared plus 4x plus 5? Doesn't it kind of sort of look similar to this? And isn't this easier to integrate? Isn't it a lot easier to integrate? Isn't an antiderivative of this just this without the derivative? Let's see. Well, let's calculate this derivative. Let's see if I'm on to something. The derivative of natural log, copy and paste, x squared plus 4x plus 5, an absolute value. Okay, a little bit of chain rule, right? 1 over the denominator, or what's inside the natural log, I should say, becomes the denominator, times the derivative of the inside, which is what? 2x plus 4, isn't it? Does this kind of sort of look like 4x plus 13 over x squared plus 4x plus 5? I think so. They have the same denominator, and they both have a linear factor in the numerator. Right? 4x plus 13, that kind of looks like 2x plus 4, not quite. I think you agree with me. I think I'm not completely crazy. Can I even do better than this, though? Can I make 2x plus 4 look even more like 4x plus 13? I think I can. I think, and here's where the algebraic manipulation comes in. Let me give myself some more room here so I'm not squeezing this in too tightly. But I think I can multiply the denominator by 2, and then what do I get? 4x plus 8, and then I have to divide by 2 or multiply by 1/2 to compensate for that. This is algebraic manipulation done correctly. And there you go. Doesn't it look a little more like 4x plus 13, at least on the inside? I would say yes. I am only off by 5 in the numerator. Okay, I've got 4x plus 8 instead of 4x plus 13. Okay. Well, 4x plus 8 is not good enough, right? I need 4x plus 13. So I'm going to force it, folks. I am going to force it. I'm going to say, you know what? This is equal to 1/2, and I'm going to force it. 4x plus 13. Ha, got it. Aha. I've got it. Only problem is I need to do the manipulation correctly. I added 5 in the numerator. I am forced to subtract 5 in the numerator. So here we go. Subtract 5. I have to do this correctly. There we go. I've got my 4x plus 13 over x squared plus 4x plus 5. But now I've got this extra 1/2 out front. That shouldn't be a problem, right? We can pull constant multiples outside of integrals, as you remember, from 114. I'm more worried about this little bonus term I got, this minus 5 over x squared plus 4x plus 5. I'm going to have to integrate this. Okay, and here's where our 114 knowledge really becomes helpful. Okay, let's look at this. I've got a constant on top. I've got an x squared on the bottom. Doesn't this kind of, sort of remind you of an arctangent integral? Kind of, sort of. That 4x is a problem, but I think it reminds me of an arctangent integral. And I know I'm always allowed to use algebraic manipulation if it helps me, as long as I do so correctly. So let me try that. Let's see if I'm on to something. And there's often an element of trial and error to mathematics. Maybe I'm on the wrong track here. That's fine. I'll try something else if that's the case. But let me try this arctangent theory of mine. What do I need with the arctangent? I need a plus 1 on the bottom, right? I need x squared plus 1. And I've got a plus 5 there, and I also have this 4x. I can at least get the plus 1 part correct. I can rewrite 5 as 4 plus 1. Okay, now I've got that plus 1 in there. And then I see, gosh, x squared plus 4x plus 4, that's a perfect square. That actually factors really nicely. Let me try it. Let me try it. 5 over, x plus 2, all of that squared. That's x squared plus 4x plus 4. It is an arctangent integral. Okay. My hunch was correct. I can integrate this now. All right. But let me back up. What am I doing? What have I done so far? I have said that this equals this. That's what I've done so far. Using a little bit of calculus and mostly algebra. I want to integrate this, the 4x plus 13 over x squared plus 4x plus 5. So why don't I continue my algebraic manipulation? Let me solve. Let me solve for 4x plus 13 over x squared plus 4x plus 5. Okay, that I can do quite easily. I isolate it. Okay, I need to multiply both sides by 2. And what did I have at the very beginning on the left? The derivative of the natural log of absolute value of x squared plus 4x plus 5. Okay, and then after I do that, I have to add this extra term I got, the 5. I should say the arctangent term, the arctangent integral. I have to add that to both sides, and sure enough, I can solve for 4x plus 13 over x squared plus 4x plus 5. That's what I'm supposed to be integrating. Okay, well, if these are equal, then the integral of 4x plus 13 over x squared plus 4x plus 5 is equal to the integral of the right side, 2 times the derivative of ln. A lot of copy-paste here. There we go. You can always use manipulation if it helps you. You can always use manipulation if it helps you. Can I break this integral up? I sure can. You can pull constants out front. Constants out front. I can separate this into 2 integrals. Just like that. And now things are pretty straightforward now. I need an antiderivative, but I'm taking the derivative. So as I said earlier, this is an antiderivative. I get rid of the d dx. Cool. And then 5 times, we've said this is an arctangent. This is an arctangent of x plus 2. And then don't forget your plus c at the end. Because I moved the 1/2 to the other side. That's why it's 2. Yeah, I'm solving for 4x plus 13 over x squared plus 4x plus 5. Good question. So I gotta move that to the other side. And then it becomes a 2. There you go. You can always use manipulation when you want to, if it helps you, as long as you do it correctly. All right. So that's what you do when you get stuck, okay? When the traditional methods don't work for you, sometimes that's the case. You can always use manipulation to help you, as long as you do it correctly. All right. This looks like a terrible 2. Let me just fix this for the record. There we go. Still doesn't look good. Slightly better. Okay. What else? What else can I teach you today? I do owe you a long division problem, don't I? That's been promised for a day now. And We can also mix up these integral problems a little bit too. This is fair. Find the area under this curve between 2 and 3. That's an integral, okay? A definite integral, okay? Now we have bounds on our integral from 2 to 3, okay? But we still have to integrate this. And this looks like a nasty integral at first, so we're gonna have to use the 5-step method, okay, to decompose this via partial fractions. Okay, we still have to do that, even though it's a definite integral. So let's go ahead. Let's give it a try. Okay, got to compute this integral. Step 1: the degree of the numerator is equal to 5. And the degree of the denominator this time is less than the degree of the numerator. Okay? For the first time, long division is required. Okay, that's why step 1 is so important. We have to ask ourselves, do I need long division or not? This time, yes, we do. All right. Maybe it's been a while since we've done long division, but I think you'll remember the dividend, the denominator. And I divide it by the numerator, x to the 5th plus x to the 4th. Minus x cubed plus x squared plus x plus 1. Here we go. X cubed goes into x to the 5th x squared times, doesn't it? X squared times x cubed is x to the 5th. X squared times x squared is x to the 4th. X squared times minus x is minus x cubed. And then x squared times minus 1 is a minus x squared. And then I stop, draw a line, and change the signs. Draw a line and change the signs. Okay, now I've got some adding. This doesn't look half bad, does it? X to the 5ths cancel out. X to the 4ths cancel out. X cubes cancel out. I have 2x squared. And then I bring down what's left, plus x plus 1. Okay, x cubed does not go into 2x squared, so I stop here. I just will acknowledge I took my numerator, I divided it by my denominator, and then I got a quotient, which I will call capital Q of x for quotient. And then I got a remainder, which I will call capital R of x for remainder. Okay. Again, I'm using P of x for the numerator, Q of x for the denominator. That's what the book does. I will follow suit. Okay, that wasn't so bad. But I need to use the division algorithm. Okay, P of x over Q of x is equal to the quotient plus the remainder divided by the dividend, okay, or divided by the denominator. Okay, I've got to use the division algorithm. So, this is what I get. This rational function is equal to the quotient, which was x squared, plus the remainder, which was 2x squared plus x plus 1, divided by the denominator, okay, or little q of x. There you go. Okay, I still have somewhat of a complicated fraction here, rational function, I should say. What I've circled on the right, I have to decompose that. Okay, I still have some work to do, but I can't forget about that x squared out front. Okay, that's a part of the answer. All right. What else? What else? I need to factor. Okay? I need to decompose. This fraction, so I'm going to factor the denominator. It's the same q of x as before, the same denominator. Okay, I think I can factor this by grouping. Maybe you learned this differently in high school. Maybe your high school is different. But this method works. I separate it into two boxes. I factor out an x squared out of the first box. I factor out a minus out of the second box. And then I say, hey, both of these new terms have an x plus 1 in common. And I factor out the x plus 1. No, Sky, it's x squared. I can factor out x squared minus 1. What is that? X plus 1, x minus 1, difference of two squares. Well, now I have two factors of x plus 1. I better consolidate that because I know we treat, in the next step, we treat things differently if we have powers. Okay? So if you can't just write it as x plus 1 times x plus 1. You need to write it as x plus 1 squared. Okay? All right. You're welcome, Sky. Step 2 is done. I have factored the denominator completely. Okay, completely. That brings us to step 3. What do I know here? Okay, so can I zoom out just a little bit now? I'm working with 2x squared plus x plus 1 over the denominator factored is x plus 1 squared times x minus 1. Okay, now I can zoom in a bit. Okay, that's what I'm working with. I just factored the denominator. That's all. What do I know? I know x plus 1 is a linear factor, so it gets a constant on top. Oh, but it's x plus 1 squared, isn't it? So I have to follow the pattern until I get a power of 2. There we go. New constant on top B. Now I have a power of 2 on the bottom. And then x minus 1, that's a linear factor. So it gets a constant on top and just one fraction there. Cool. That's the new part. The rest is review. The rest you know how to do. Okay? The next thing we do is we kill the fractions. We kill the denominators. I'll get to the x squared in just a moment. Yeah, we can't forget about the x squared. But I have to decompose. I have to decompose this fraction. Okay? It's x squared plus a fraction I have to decompose. Okay, that's what I'm doing now. But I mustn't forget about the x squared. Okay, we multiply both sides by the least common denominator. Nice little trick, kills all the fractions. And then we can equate the coefficients by solving, and then solve, a system of equations. We know how to do that. I will leave that for homework, okay? I promise you A is 1. I promise you B is minus 1. And I promise you C is 1. Okay? I'll leave that up to you. Just because 50 minutes go so fast, I don't have time to do everything, sadly. But you do know how to do this. All right. That is step 4. Okay, I'll bring in the x squared now in step 5. Here's what we started with. Okay, I'm going to summarize everything we've done. We started with this beast of an integral. Then I didn't decompose it so much. I used long division. And I broke it up. Okay, I've got the x squared there. And then I have a rational function where the degree of the denominator is larger, so I can use the partial fraction decomposition technique. Okay, so I did that. What was the first thing I did? I just factored the denominator. And then I decomposed it. Do you have to repeat all of these steps when you're doing your homework? No, I'm just summarizing for you, okay? I'm just summarizing everything I did. And then, unfortunately, I had to leave it for homework, but we all know how to find A, B, and C. Okay, that's solving a system of equations. I promised you that these were A, B, and C. They are correct. And then we've got a pretty reasonable integral on our hands. Okay, x squared, 1 over x plus 1. None of these terms in the integral are difficult to calculate an antiderivative for. So, unfortunately, I'm sorry, 15 minutes goes way too fast. But this is the integral. Okay, but you can do this. Fundamental theorem of calculus. Find an antiderivative, plug in 3, plug in 2, take the difference, and you will get this, I promise. I see a question. Do we really have to do long division? Since 5 minus 3 is 2, we already know that the constant remainder has degree 2. So we can, you do have to do long division, yeah. You do have to do long division. Which makes it a lot of work. Maybe you don't like long division. It is required, yes. And the reason is we really need the degree of the denominator to be larger than the degree of the numerator. Otherwise, the stuff that I'm teaching you doesn't work. Okay? Doesn't work. So we do long division, and then we do get the degree of the denominator to be larger than the degree of the numerator. Okay? Then these 5 steps work. Good questions. All right. And again, check. You can compute that integral. You can do that. You might be a little rusty, but you can do it. Okay? You'll be very much not rusty once you do this homework. Okay? You'll get all your 114 stuff back if you've lost anything. All right. So there, as promised, is a problem where we have to do long division. All right. What else can I do to prepare you for the homework? Yeah, you'll get what I call hidden partial fraction problems. Okay, something like this. Find this integral. Well, this isn't a rational function. Okay, this is not a rational function. E to the 2x plus 4, e to the x. That's not a polynomial. E to the 2x plus 3, e to the x plus 2. That's not a polynomial. This is not a rational function. But it kind of looks like one, right? Kind of, sort of looks like one. So maybe our techniques would work for this. Not exactly, but maybe I can do some sort of manipulation, there's that word again, to help me. And maybe I can do that. Here's my idea. Remember learning U substitution in 114? That's what I'm going to do here. I'm going to use a U substitution. The course notes use the letter K instead of U. I will follow suit, okay? I will use K, but really you can use any letter you want, just not X, because that's the variable that we're playing with, okay? So let K, and if you want to use U, that's fine. Let K equal e to the X. Okay, I think if I do that, and I can transform this integral into in terms of K, and then I think it will look like a rational function, and then I think my 5-step method will work, okay? Let's see, though. Once you let K equal e to the X, I need to take derivatives, right? Remember that from U substitution. I needed to take the derivative of K here with respect to X. Well, that's just e to the X. So dk is equal to e to the X dx, if I can squeeze that in. Okay, you remember this technique from, this is U substitution. That's all this is. All right. Let's see here. So if I do that, what do I get? Well, I am going to go ahead. I'm going to do a few things at once. Don't forget the integral sign. But I'm going to factor out an e to the x in the numerator. Okay, I see I can do that. I can't do that in the denominator, but I can do that in the numerator. So I get what? E to the x plus 4, huh? And the denominator, I don't have to do this, but I could write e to the 2x as e to the x, all of that squared, plus 3e to the x plus 2. Okay, don't forget your dx. And then, let's see here. What does this equal? Well, e to the x plus 4, but I'm letting e to the x equal k. So this is just k plus 4. Okay. What about the denominator? E to the x squared? Well, that's just k squared. Plus 3 e to the x, that's just plus 3k plus 2. Okay. And now check this out. When you do this u substitution or k substitution, if you will, you need a perfect match. What about this part? What about e to the x dx? Well, e to the x dx I know is dk. I've got this perfect match. Okay? We need this perfect match for this u substitution or k substitution. I have the perfect match. E to the x dx is dk. Cool. Remember that u substitution or k substitution, if you will. Folks, I can decompose this. This is a rational function now. I can decompose k plus 4 over k squared plus 3k plus 2. It's a rational function now. Okay, so we can combine these techniques that I'm teaching you today and yesterday with some other integration techniques from 114, namely u substitution or k substitution in this case. That's cool. Okay, you can combine your knowledge and use it to calculate more complex integrals. Okay, but it's not so complex now, is it? We can do this. All right, let's do this. Well, the degree of the numerator is 1, right? K plus 4 has degree 1. The degree of the denominator, k squared plus 3k plus 2, is 2. Degree of the denominator is larger, so no long division this time. Okay, we do not have to do long division this time. Okay, step 2, same 5 steps once you start decomposing. Can I factor the denominator? I sure can. Not so bad. Quite easy this time. It's reducible. It's a reducible quadratic. Okay, that's part of the value of part 2. It forces us to address whether or not that quadratic in the bottom is irreducible or not. Okay, it is not irreducible. It's reducible. Reduces to linear factors. So I know how to decompose it in step 3. Okay. I've got 2 linear factors in the denominator. K plus 1, so it gets a constant on top, an A. X plus 2 is linear, it gets a constant on top, B. Ashley, what if the degrees are equal? Then you need long division. Yeah, you need long division. Shall we back up just a little bit? Just to put your question into proper context. Yeah, use long division. Step 1, use long division if the degree of the numerator is greater than or equal to the degree of the denominator. So, Ashley, if they are equal, then we have to use long division. Yep, good question. Okay. But that's not the case with our current function. Where is it? There we go. Yeah. Here the degrees aren't equal. Here the degree of the denominator is larger, so no long division required. Okay. Step 3, I think that might be the hard part. That's the new part, at least. Okay, after that, everything else is stuff from the past. We know how to multiply both sides by the least common denominator. We know how to kill all the denominators, kill all the fractions. Okay. What do I get when I do that? I get k plus 4 equals a times k plus 2 plus b times k plus 1. We know that. Then you know to equate the coefficients, okay? So I simplify the right side. Now I can see, all right, a plus b has to equal 1. And 2a plus b's got to equal 4. It's the only way I get equality there. Well, now I have a system of equations that I must solve and check, right? That's required in this class. The proposed solution you get is not enough. You have to verify that, yes, your proposed solution was indeed correct. Okay? Unfortunately, I have to leave that for homework again. But you can do this. This is an easy system to solve. Okay? A is 3, B is minus 2. We can even check right now. 3 plus minus 2 is 1. 2 times 3 is 6, plus negative 2 is 4. Yeah, this is correct. This is correct. All right. Well, that's step 4 then. Step 5. Compare this with step 3. Let's zoom out. I'm rewriting k plus 4 over k plus 1 times k plus 2 as a over k plus 1 plus b over k plus 2. But hey, I know a is 3. I know b is negative 2. So I go ahead and write the minus out front, make it a subtraction. I'm good to go. Okay? And these are supposed to be k's. Excuse me. All right. Well, this integral, this we can calculate. This we can calculate. It's going to have some natural logs, isn't it? 3 times natural log of absolute value of k plus 1 minus 2 natural log absolute value of k plus 2. Don't forget the plus c at the end. And hey, we've got a solution. We've got a solution. What's the problem with our solution, folks? What's the problem with this? I haven't done anything wrong yet. But this answer is not quite correct, despite the fact I haven't done anything wrong yet. What do I have to do? Do you remember from 114? Yeah, get in terms of x, okay? Yeah, replace the e to the x back in. Awesome. So we're not done. The final answer must be in terms of x because that's what the original question was in terms of. That's fair. Okay. So, recall we set k equal to e to the x. Yeah, Sky, the problem's k. Yes. So I go ahead and do that. K, I sub back in e to the x, 4k, excuse me. There you go. Just wait a minute. E to the x plus 1, that's never going to be negative. E to the x plus 2 is never going to be negative, so I don't even need those absolute values. Okay, I don't need them. So I can get rid of them. There you go. There's the integral. There's the integral. A little bit of substitution from 114 combined with these partial fraction decomposition techniques from 124. Cool. All right. Let's see. What else can I do for you today? It's the last lecture. I think we do have time for this problem. Compute this integral. Compute this integral. Let's give it a try. Well, the degree of the numerator is definitely 4. The degree of the denominator I have to think about. You know, when I square the x squared plus 2, I'm going to get x squared times x squared. I'm going to get an x to the 4th term. And then I'm going to multiply that with the x plus 1. Then I'm going to get an x to the 5th term. So the degree of the denominator is actually 5. So no long division required. Okay? No long division required. Can I factor out the denominator any more than it is? No. X plus 1 doesn't factor. X squared plus 2 doesn't factor. The denominator, folks, is already factored. All right. So I've got a mix here. The x plus 1 is a linear factor. The x squared plus 2 is an irreducible quadratic. An irreducible quadratic. It does not reduce. It does not factor. Okay, so I know how to do the decomposition. X plus 1 is linear, so it gets a constant on top. A over x plus 1. There's no power on the x plus 1. Well, a 1 technically. So I get 1 fraction. Okay. The x squared plus 2 is irreducible. It gets linear factors in the numerator. Okay. The power of 2 indicates there are 2 fractions. bx plus c over x squared plus 2 plus dx plus e over x squared plus 2 squared. Okay, following the same pattern we've been following all along. Okay. This one has, God, we're going to have to solve for A, B, C, D, and E with this one. You see that? We've got 5 unknowns here. This system is not going to be a piece of cake to solve. We can do it, though. The same steps work every time. What do? Kill all the fractions. Multiply both sides by the lowest common denominator. Least common denominator, whatever you want to call it. Multiply both sides by the least common denominator. Okay? This is what you get. Okay? This is what you get. Ignore the colors for now. But this is what you get. It's a little messy. I know. It's because we have 5 unknowns. Okay? Multiply both sides by the least common denominator. And then you know what to do next. Let's simplify the right-hand side. Okay? That's a little tedious too. I'll save that for homework for you. I promise you this is correct, okay? We just expand everything, collect the x to the 4th terms, collect the x cubed terms, collect the x squared terms, collect the x terms, and collect all the constant terms. And there you go. That does take some work, okay? And we have to be so careful. It's easy to make a sign error or a silly arithmetic error. So be wide awake when you do this stuff, okay? Wide awake. All right. Now you can see, hey, we've got a system of equations to solve. I've color-coded this. Can I zoom in a little more? Not really. But I see a plus b has to equal 1, right? The coefficients of x to the 4th on the left and right side have to be equal. A plus b's got to equal 1. Okay? B plus c has to equal 0. Okay? There's technically no x cubed term on the left side, although we could force it and write plus 0x cubed, as I did. You don't have to. Okay? B plus c has to equal 0 because there's no x cubed term on the left. Okay? 4a plus 2b plus c plus d has to equal 5. The coefficients of the x squared terms have to equal. Okay? 2b plus 2c plus d plus e, that needs to equal 1. Okay? I do have an x term, a single 1x on the left. And then I know 4a plus 2c plus e needs to equal 4. The constant terms need to equal. Okay? To summarize everything, comparing the coefficients, we call this, as mentioned yesterday, I need to solve this system of equations. I need to solve this system of equations. I said a plus b has to equal 1. There it is. I said b plus c has to equal 0. There it is. I said 4a plus 2b plus c plus d needs to equal 5. There it is, okay? And I've organized this pretty well. Okay, I've got my b's in a column, my a's in a column, my c's and d's and e's all in a column. I recommend doing it this way. Okay? I recommend doing it this way. Folks, I don't know if we've seen this before where we've had 5 unknowns. What is the best way to solve a system of equations with 5 unknowns? Well, that's somewhat of a subjective question, right? The answer is going to vary from person to person. Here's my answer. I'm going to use matrices. I am going to use matrices. I don't like all of these unknowns. The A, the B, the C, the D, the E is too much. Okay, so I'm going to use an augmented matrix instead. And I'm going to get this augmented matrix in row echelon form. Okay, and then I'm going to do back substitution. And then I'm going to get a proposed solution. And then I'm going to verify that proposed solution. Okay, quite easy to make a silly mistake with a matrix this big. Okay, we have to be wide awake when we do this. Okay, wide awake. Okay, I'm going to get in row echelon form and back sub. And then I'm going to check. I should write that too, and check. Or verify, if you will. I'm going to verify my solution. It actually works out. Okay, it actually works out. I only have 2 minutes. I knew I wouldn't have time to go in detail with this. But this is something we know how to do and can do. Okay, we can get this in row echelon form. We can do back substitution. And we can check our solutions. All right. Then, we're not even done at that point. If we know what A, B, C, and D, and E are, then we can plug those values into the integral. And that's not a bad integral to calculate. Okay? It's not a bad integral to calculate. Okay? So this problem is no different than any of the others I've shown you, except for the fact that the solving the system of linear equations part was a little messier than average. Okay, I had 5 unknowns. Other than that, it's the same 5 steps. You know, I still have a 5 on the top left. Okay, I still do step 5 after step 4. Okay. All right, I've got 1 minute left. So let's do some recap trivia. Okay. Let me know in the chat, folks. I think this was addressed already. I'll ask it anyways. To calculate the integral of p of x over q of x dx, excuse me, we must use long division if the degrees of the numerator and the denominator are equal. True or false? And again, we're assuming this fraction is simplified. Okay, true, 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 true. Anyone else? I think there's a consensus. It is true, okay? It is true. In fact, if the degree of the numerator is greater than or equal to the degree of the denominator, we have to use long division. Cool. Very good. What else? To calculate the integral of some polynomial p of x over some polynomial of the form ax squared plus bx plus c dx, we must always use the following decomposition. Okay, I see what's going on here. They're saying it's a quadratic factor on the bottom, so it will get a linear factor ax plus b on the top. Is that true or false, folks? What do you think? We have a true. Anyone else? Have I stumped you? There's less answers on this one. It is time to go, so if you do have to go, I understand. But if you want to stay with true, Ashley says false. Tinashe says false. Yeah. Is it Ivan? I'm sorry. I think it's Ivan. If my Afrikaans is not great. Can't we factor? I agree. I agree. I never said this was irreducible. Okay, so it is false. The reason is ax squared plus bx plus c could, sorry, that's a u, could be reducible. Okay, could be reducible. So very good. Yeah, Josh, you've nailed it. Yeah. Only if it's irreducible does it decompose this way. Okay, only if it's irreducible. If it's reducible, then we actually have two linear factors, and then you know that decomposes quite differently. Good. Okay. True or false? All of our 114 knowledge will be very much, if I can read correctly, will very much come in handy for this section. True or false? All of our 114 knowledge will come in handy at some point for this section. Ian says false. False. Ivan is fine. Okay, thank you. We do have one true. Yeah, what I will say is I will rephrase it. All of the integration and differentiation topics, definitely. Differentiation, let me spell correctly, topics will come in handy. I calculated some derivatives. I calculated plenty of integrals. I used the substitution. I used arctangent. So maybe not all, but definitely a lot. A lot will come in handy. So depending on how you interpreted that question, yeah, true or false is okay. Folks, that's all I've got for you. Tomorrow, you begin chapter 3. And tomorrow that will be with Dr. M again. But I will see you again in chapter 5. So, as usual, I have to apologize. I have a tutorial after this I have to get to. So I can't stay afterwards any further. But you know how to reach me via email and Discord. So reach out to me if you have any questions. Otherwise, we'll see you again in tutorials on Discord and again in chapter 5. Take care, everyone. Bye-bye.